École Normale Supérieure de Lyon. He finished it by 2003. From 2003 to 2006, he made a number of postdocs in Geneva and Toronto, EAGS. He had positions in Orsay, INS Paris, as a chargé de recherche. And since 2016, he is in the Université de Cergy-Pontoise as a director de recherche do CNRS. So the research of Bertrand touched several different topics: laminations by Riemann surface, groups of circle diffeomorphisms, Brownian motion on foliated surface, branched projective structures, and holomorphic foliations. So his research is not only deep, but also extremely original. Today, we are going to witness this originality by listening to Bertrand, joint work with Álvares, groundbreaking work on the dynamics of Jouanolou foliation. So sit back, relax, and enjoy.
Thank you very much, George, for this introduction. I am very honored to give this plenary talk. And so, as George was saying, I will present a work in collaboration with Aurélien Álvares on the dynamics of the Jouanolou foliation. But I would like also to take this opportunity of giving a plenary talk to report on the theory of differential equations on surfaces, on the real case and on the complex case. So I am going to begin with the real case and to state some kind of classical theorem that will illustrate also the complex case that I will describe later on the talk. So the first theorem I would like to mention, and probably most of you know this theorem. This is a theorem that dates from the late 19th century, I mean, but was proven by Poincaré and Bendixson, which states that the trajectories of a differential equation on the plane, so you take a differential equation of that form on the plane. So here P and Q are some smooth functions, say. So suppose you take a bounded trajectory of such a differential equation, then it will be defined for all time because it is bounded, and it is going to accumulate on a limit cycle like this, or on a singular point, on an equilibrium position, or maybe a kind of cycles of saddle connections, or graphs of saddle connections. So you could have such a situation where your trajectory is going to accumulate on such a graph of saddle connections. So saddle connections are trajectories which between two singular points of or two equilibrium positions of the singular differential equations. So in fact, if you consider differential equation on the plane, or it also works if you consider the same theorem works for differential equation on the sphere. So the situation is pretty simple. Let just me mention that there is a kind of, there are plenty of open questions still on this question, which are related to the 16th Hilbert problems, which ask for if P and Q are algebraic functions, so polynomials of degree D polynomials, say degree 2 polynomials, we don't know the answer. So the question is, what are the positions of the limit cycles on the plane that you can see for such differential equations? So we don't even know if the number of such limit cycles is bounded in terms of the degree. We know these limit cycles is bounded for a given equation, but so there are plenty of questions still that goes back to Hilbert, but I will not speak more about that. Just I wanted to say that this is something which is still kind of open. What I would like to do now is to go to other surfaces, so not to take a higher-genus surface, for instance. And there is a theorem by, so we know that for higher-genus surfaces, you can have some much more complicated dynamical systems. For instance, quasi-periodic dynamical system of flow on a torus. But there is a theorem by Mauricio Peixoto in the 60s that says that if you take a generic such differential equation on any compact surface, then in fact you will see this behavior. Namely, you will see a finite number of periodic trajectories. All such trajectories are hyperbolic, so they are either attracting or repelling. And you don't have saddle connections, so these kind of things do not happen generically. You can break, by perturbing the equation, you can break such saddle connections. And equilibrium points are hyperbolic, and there is no recurrence, meaning that all the trajectories they are accumulating on periodic trajectories or equilibrium points, as in the pictures. So such systems are called Morse-Male. And Peixoto proved that generic vector fields is Morse-Male on a surface. And in fact, he also proved another result, which is extremely interesting, which is that these systems are what we call structurally stable. So the definition of structural stability goes back to 30 years before, to two Russian mathematicians, Andronov and Pontryagin. And so what they did is that they really thought, I think the idea was very important, because they really thought of a differential equation on a surface as a geometric object. So you just forget about the time parametrization of the solution. You just keep the integral curves that decomposes the surface into a family of those integral curves. So you can draw these pictures, and the structural stability is that if you perturb your equation a little bit, then the picture is not going to change up to homeomorphism. So I think really so there are two things, but really to think of these objects as geometric objects is very important idea that comes, I think, back to these two Russian mathematicians. And so what proved Peixoto is that, in fact, the Morse-Male vector fields are exactly the structurally stable vector fields on a surface. So this is a very important theorem. And so, in particular, a generic vector fields on a surface is structurally stable. And I think there are, so kind of end of the story in a sense, but I think there are still very interesting questions, and I will kind of mention them because I think they will illustrate the purpose of my talk when I will go to the complex case. So what you can try to do, and I think there is something which is extremely interesting and not completely understood yet, is that you can look at this set of structurally stable vector fields on the surface. So this is an open set in the set of all vector fields on the surface. And in fact, this set is this is an open set in a Banach space. It has a very interesting geometry, I think. And in particular, you can try to cut and to consider finite dimensional families and try to understand and to make pictures of that. So let me just show you one of these pictures. So this picture is due to Arnold. Let me just, sorry. Yeah. OK. So if you take a differential on a vector field differential equation on a torus, you might consider those that are transversal to such a fibration by circles. So namely, the trajectories are transversal. There is no, I consider the case where there is no equilibrium point, neither. And so if you consider such kind of equations that are transversal to a fibration like this, in fact, understanding the dynamics of such an equation is the same as understanding the first written map to a given fiber. So you take a point x in a fiber, and you start the trajectory and you look at the first return point. First time you return to the given transversal, you get a diffeomorphism F is the first return map. It is a diffeomorphism of the circle. And so you see that the theory of differential equation on surfaces is extremely related to the theory of iteration of diffeomorphism, because of course if you continue the trajectory, you will see the iteration of this F. And so Arnold has studied this family of diffeomorphism of the circle. I mean, you can go on the other way around. Given the diffeomorphism of the circle, you can construct a vector field on a torus such that the first return map is your given diffeomorphism. And so Arnold studied this family, this very famous family that he studied. And so you see it depends. So it is a map from the real numbers to the real numbers, but it commutes with the integer translation. So in fact, it defines a map from the circle, the real divided by the integers, to itself. So you can consider this family of diffeomorphisms of the circle that depends on the two parameters alpha and epsilon. Okay? And in yellow, what you see, so in yellow, those are what is called the Arnold tongues. So those are some open subsets. And in fact, the union of all these tongues is exactly the stability locus for this family. You see it has a very interesting geometry. And in fact, in this case, we can prove that this is a dense open set, but it has not total Lebel measure. This is what is called the CAM phenomenon. And in fact, just this question, for instance, I think is completely open yet, and also the study of the geometry of these stability locus. So I just wanted to mention also these problems that I think are very interesting in the real case. Okay, let me go to the complex case now. So in the complex case, the situation is drastically different in the sense that you see complex differential equations often are completely chaotic. And one of the first breakthrough in the theory of differential equation was the theorem of the Russian school in the 60s, theorem by Uday Verenov in 62. What he did is that he considered polynomial differential equation, as in the theorem of Poincaré-Bendixson, but here the differential equation is considered in the holomorphic sense. So T is a complex time. Okay, so the solutions of this differential equation are immersed complex curve in C2. And what he proves is that these integral curves are dense when P and Q are chosen generically as degree D polynomials. So it's completely different, and it's drastically different as in the real case where we see these very simple dynamical systems. And in fact, this theorem by Uday Verenov was complemented by Ilyashenko some years later, so in 68 and then in 78. So what Ilyashenko proved is that, so more than the fact that the orbits are dense, is that the differential equation is ergodic, which means that you cannot find even a measurable function in the UV variables that are constant on the solutions and that is not constant globally. So it is the meaning of ergodicity. And it is also locally rigid, which is the opposite of structural stability in a sense. That means that if you take such a differential equation, a generic differential equation like that, and you perturb the coefficients P and Q, you will see a phase portrait which is topologically completely different than the original phase portrait in the complex case. So those two theorems show that, I mean, in the complex case, you see some chaotic systems. And in fact, the story goes on so this theorem was complemented by many people in the last 60 years. And maybe it was culminating by a theorem, the end of the story about these things was a theorem by Franck Lorrain and Julio Rebello in 2003 that was also valid in higher dimension. So what they did is that they considered foliations on the complex projective spaces, which are obtained from the affine space C to the n by adding a complex, so inductively by adding a complex projective space of dimension 1s. And in fact, they proved that in these parameter spaces of degree D algebraic foliation on these projective spaces, there exists an open and non-empty subset of foliations having the same property as in the Udai-Zverenov and Ilyashenko theorem. So really the difficulty to go from Ilyashenko and Udai-Zverenov theorem to the Lorrain and Rebello theorem is that in Ilyashenko and Udai-Zverenov, they considered a foliation on the plane. And what they do is that they compactify the plane by adding a line at infinity. And in fact, they observe that if P and Q are generic, this line at infinity, I mean, you can extend the foliation as a algebraic foliation, which will have the line at infinity as a leaf. So you will see some singularity at infinity, and the foliation will look like that. So here you have the complex plane, C2, on the complement of this line at infinity. And in fact, their theorem, the main tool to prove their theorem is to consider the monodromy of this line at infinity, the monodromy induced by the foliation. And in fact, in the family considered by Lorrain Rebello, the family of foliation is bigger. So you really considered, you start with a foliation of P2 of the complex projective plane, for instance. And a priori, there is no guarantee that this foliation will have a line which is invariant, as in the case of Udai-Zverenov and Ilyashenko. So this is kind of the difference. So the difference is that the parameter family of foliations considered by Lorrain Rebello is larger than the family considered by Ilyashenko and Udai-Zverenov. So basically, the idea to establish this kind of theorem is to try to establish that you can find transversal disks to the foliation and first return maps defined on some open subsets of these transversal disks. So you will find a map that is a first return map of the differential equation, and which is going to map the domain of definition of that map to a domain which is very close, and the map on the restriction of on its domain of definition is very close to the identity also. So you can consider this kind of first return maps that are close to the identity, and really the idea to try to prove that the orbits are going to be dense and these ergodicity properties and also the rigidity is to observe that if you have such a map which is close to the identity, and if you have two such maps, say H and K, then you can consider the commutators, which is also a kind of first return map associated to the foliation. And this map is going to be much more closer to the identity than the original H and K. And so by taking iterations of commutator, you are going to prove that you can construct maps that are closer and closer to the identity. And this explains why the orbits are dense, because you will have the orbits are going to be given by some, I mean, if you have a point in an orbit, you will have some points in the same orbit that are very close to that point. And using this kind of idea, you can really prove that the orbit is going to be dense. OK. So this is the theorem of Loret and Rebello. In fact, so the foliations that they construct, to go back to the idea that I spoke about at the beginning of the talk, they really construct foliations that are an open subset in the moduli space of foliation that is contained in the bifurcation locus, namely all these foliations are locally rigid. And the question was whether this bifurcation locus was everything, as in Ilyashenko and Udai-Zverenov's theorems, or if it is really strict. So what proved with Aurélien is that, in fact, there exists a non-trivial stability locus. So both phenomena of bifurcations and stability, you can see them in the moduli space. And this phenomenon will have non-empty interior. So there will really be, both will be present in the moduli space. So our theorem is the following. So in fact, this is a theorem that we proved in the degree 2 case. Conjecturally, we have the same statement in any degree, but we don't have a proof yet. So you consider this foliation that has been introduced by Jouanolou. So it is defined, you take this differential equation in the 3 variable x, y, z in C3. And as you observe, it is a homogeneous equation of degree 2. So the foliation induced by that foliation on C3 is invariant by multiplication by the scalars. And so you can quotient that foliation to a foliation defined on the projective plane. And so in fact, it was introduced by Jouanolou in the 70s to prove, in fact, Jouanolou proved that this foliation have all its leaves that are transcendental curves in the projective plane. And so it enabled Jouanolou to prove that the generic foliation of the projective plane has this property of having all these leaves transcendentals, a property that you can deduce from the theorem by Loret-Rebello that I just mentioned before, but that was proved much later. Anyway, so this foliation was introduced by Jouanolou, but what we proved is that this foliation is structurally stable. And moreover, we proved that it has a kind of interesting dynamics. It has two parts in its phase space. It has a part which is extremely simple. You have it is completely integrable. You have a first integral on an open set, defined on an open set. But this open set is not the whole of P2. Its complement is a very thin set. It has a Lebesgue measure 0. But on this complement, the dynamics is chaotic. So we know well that in the theory of one-dimensional dynamical systems, we have this kind of phenomenon that you have a set where the dynamics is very simple and which have full measure, and a complement of 0 measure where the dynamics is completely chaotic. So this is exactly what happens here. So in the jargon of dynamical systems, one holomorphic dynamical systems, so you have you can decompose the phase space in a set, as I said, which is called the Fatou set, where the dynamics is kind of very simple dynamics, integrable, or you can understand very well. You have a complete classification of the dynamics on these sets, and the Julia set, where basically the dynamics is chaotic. But it turns out that often those Julia sets have 0 Lebesgue measures, so they are very thin. And those are open subset of the parameter set where having full measure. And so, so this is exactly what happens also in this situation. You have a FATU component, non-trivial FATU component. So you have an open set, subset in P2, having full measure. And on this open set, so this is what we call saturated by the foliation. I mean, this is a union of leaves of the foliation. On this open set, you have a first integral, so namely a function which is constant on the leaves. And this function is holomorphic and takes values in an algebraic curve. So it's in a Riemann surface, which is a Klein quartic. So this is this algebraic curve that I just I wrote the equation of that curve here. So this is the equation of that curve in the x, y, z coordinates. And in fact, this is an extremely nice algebraic curve of genus 3. And this is, it can be characterized by the fact that it has a very large, it has a larger automorphism group among the Riemann surfaces of genus 3. And I draw here, I mean, you can, the tessellation of the quotient of that curve by its automorphism group. So this is a tessellation that you can find in the book of Klein. This is a curve that has been studied by Klein. So this is a uniformization of this quartic by the unit disk that has been founded by Klein in the 19th century, around 1860, in 1870. Sorry. So you see that to come back to that Jouanolou foliation, you see that it has this FATU component. It has a kind of simple dynamics on that FATU component. This component has full Lebesgue measure, but its complement is a set which is extremely interesting of zero Lebesgue measure on which the dynamics is completely chaotic. So we don't have any results concerning the dynamics of the foliation on that Julia set. This is called the Julia set of the foliation. But we have some conjectural we have made some experiments that can show that this the dynamics of this foliation on this Julia set is related to other kind of dynamical systems, namely the Lorentz attractor. I will give you a picture and I will give a finite conjecture at the end of the talk. Let me just give you some idea of how we can prove such a result. And in fact, the proof, the main ingredient in the proof of such a theorem is to consider what we call the gradient vector field. And the difficulty, so say if you want to prove structural stability for such a dynamical system which is chaotic, the difficulty here is that this is not a classical dynamical system. I remember that the orbits of the dynamical systems are complex curves. So they are two-dimensional curves, and so it's not a classical dynamical system because we don't know in which direction we should go to study the dynamics. And in fact, to establish structural stability, we have, so the theory is very well developed for classical dynamical systems. It was theorems on the 60s and 70s. Beginning by Anosov and Smale. So they proved that there are a whole class of dynamical systems that are chaotic and structurally stable. So these are the hyperbolic dynamical systems, or first class also is Anosov dynamical systems. And there is a full list of results and works of this period to give conditions to ensure structural stability in the classical case, namely for a flow, say, or for a map that you iterate. And here we don't have a classical dynamical system, but our idea will be to to find a classical dynamical systems and to use, to prove that it is structurally stable and to deduce back the structural stability of our foliation. So this dynamical system is a flow, and it's generated by a vector field that we call the gradient vector field. So let me just, this is really the main ingredient, new ingredient that we introduced in this story. So to introduce this gradient vector field, I'm going to present a general criterion of structural stability for a foliation of the projective plane. So you start with a degree D foliation of the projective plane. And in fact, it is always defined by a homogeneous vector fields of degree D on C3, exactly as the Jouanolou foliation was. And this vector field is not well defined because you can add a multiple of the gradient vector field. You don't change the projectivization of that vector field, so your foliation. And adding a multiple of the gradient vector field, you can always assume that the divergence of V is 0. It's a complex divergence. So this is defined by this formula. So those are the complex derivatives, the partial x, partial y, and partial z with respect to the x, y, z variables. And so we are going to assume that we have this homogeneous vector fields on C3 of 0 divergence. And the criterion is the following. So in fact, the important thing to consider is to consider the function which is essentially the Hermitian norm on C3. In fact, we take the logarithm because it will be better to define this gradient vector fields. And our criterion is the following. If you consider the restriction of this function to the singular curves, to the integral curves of the vector fields V, you want that function as only local minima as critical points, non-degenerate local minima. In fact, it is easy to see that. So you have three possibilities. So you restrict a function on a surface. So it's critical points. Generically, they can be local minimum or saddles or local maximum. Here, local maxima are not possible because this function f is pluri-subharmonic, strictly pluri-subharmonic, and you restrict it on a holomorphic curve. So you cannot have a local maxima, but you can have the two other possibilities, or a saddle or a local minima, and we assume that we always have a local minima. So essentially, this is a kind of thing which is really easy to verify. This is an algebraic equation. I will explain later the kind of equation that you get. And in fact, this is exactly this condition that will ensure structural stability and the existence of a Fatou component having a first integral on a compact Riemann surface of that genus with this formula. So this is a good place to define this gradient vector fields that I was speaking about before. So these gradient vector fields, this is a vector fields on C3, but in fact it will be invariant by multiplication by the complex scalars. So it will descend to vector fields on P2, and it is defined as the gradient of the function f along, so not the whole gradient, but you restrict the function f along a solution, a V trajectory. And you take the gradient of this restriction. So you take the gradient of that function f along the v trajectories. With respect to a convenient Hermitian metric, which is not really important in the purpose, you just choose one in such a way that this gradient vector field is invariant by multiplication by the scalars. And in fact, what you can establish very easily, and in general, without assumptions, in general, this gradient vector field will have a very interesting hyperbolicity property, which is that the trajectories of these gradient vector fields along a leaf of the foliation. So if you take a leaf of the foliation, which is a Riemann surface, so it is a surface, so say a disk, in fact, the leaves, the trajectories of the gradient vector fields are escaping from each other. So we have an instability of W along the direction of the foliation. And in the transversal directions, so say it is a transversal disk of the holomorphic foliation F, in P2, you have a contraction. So you have these hyperbolicity properties. So transversally, we have a contraction. And tangentially to the foliation, we have an expansion. So in fact, you see that, and this is completely general. There is no assumption here. You can establish this property completely generally. You see that the leaves of the foliation are unstable leaves for these gradient vector fields. Now, if you know a little bit the theory of the stability for vector fields, you will see that you will be able to, you will have hyperbolicity property, you will be able to get them if you have also some transversality properties for your vector fields, because you have to so the difficulty once you have hyperbolicity, the difficulty is to treat the singular points of the vector field W. So W will have lots of singular points. It will have the singular points of the foliation. You have many singular points. You have d squared plus d plus 1 singular points coming from the foliation. But it will have also another family of singular points that are in the regular part of the foliation, and that forms an analytic surface in P2. And in fact, this singular point, this is what is going to make the instability or the stability. And you see that these singular points are exactly the critical points of the restriction of the function f to the trajectories. So with that assumption, you are able to apply the theory of stability and to deduce the stability of the foliation to have a kind of idea of what happens. So of course, you have to work a little bit more, but it's the main idea. So for instance, to see what is this criterion in the case of the Jouanolou foliation of degree 2, I call it Jouanolou 2 here, you see that you have to, so this, sorry. How does it work? Anyway, so the first inequation, so the second equation here is the equation of the critical points of the norm along a trajectory. It's extremely easy to establish. And then you have to verify that all the critical points that you get, they are local minimum. And to see the condition to see if a function on a surface has local minimum, if a critical point of a function on a surface is a local minimum, it is just an inequality on its derivatives. And this inequality is just the first equation. So in fact, to prove that Jouanolou in degree 2 satisfies our criterion is just amount to prove that you have this first inequality, which is an algebraic inequality of degree 4, on this real algebraic manifold of P2. In fact, this real algebraic manifold, it is what is called a mixed curve, because it involves, in its definition, it is defined by a polynomial in the holomorphic variables x, y, z, and also their conjugate. And you have both a degree for both of them. So this is a very interesting object, I think. that was studied recently by Matsuo Oka, and in fact we use a little bit of this theory in our argumentation. For instance, to really understand what is the genus of this surface. So the genus of this surface is exactly written here. This is the surface. So this surface that whose equation is here is exactly the quotient space of the foliation at the end of the story. So it has this genus. So we have to compute this genus, and we can use some tools coming from this theory of Matsuo Oka. Okay, so I don't want to say more about this. Just what I wanted to say is that we try to, so concerning this idea that I wanted to keep in my talk of studying moduli spaces of differential equation on surfaces, real or complex, and studying the dichotomy between stability and versus bifurcation. We would like to draw some pictures in the moduli space of degree 2 foliations of the complex projective planes, say, and to draw these stability components, say the Jouanolou stability components, and to draw the instability bifurcation locus given by the theorem by Loret-Rebello, for instance. But it's kind of, it's a challenge to draw and to see how to make computer experiments in this vine. So the thing is that we don't have any picture of the stability locus, and I wanted to show you some other kind of dynamical system differential equations which are linear, for which we know how to compute. We have pictures. So those are linear differential equations. And in fact, if you consider these linear differential equations, so you have a second order linear differential equation, of course you can make it a first order differential equation by taking a new variable which is a derivative of v with respect to t, right? As usual. So you have this differential equation that are defined that depend on two polynomial p and t of one variable, one complex variable. So t is a complex variable. And in fact, this differential equation, you can in fact projectivize this differential equation and study and get differential equation on complex surfaces which are ruled surface over the t variables. So those are surfaces that are vibration by projective curves, and you can ask. So they define families of foliation on these surfaces, and you can ask the question of describing the stability locus versus the bifurcation locus. And this is what you get. So here in red, you get all the stability components. So this is an image that has been produced by David Dumas. You can find it on his web page. There are plenty of other very nice pictures. So you have all these components of stability, and the black region is a region of bifurcation. It has also non-empty interior, exactly as in the theorem of Loret and Rebello. And just to say what happens, so in fact, this differential equation, of course, they have been studied since the early 19th century by Riemann and Fuchs, Klein, blah, 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 all these people. And in fact, this story of stability ended up with Sullivan that completely characterizes the equations that are, those linear equations that are structurally stable. In fact, the theorem of Sullivan is a theorem about the stability of the groups of Möbius transformation acting on the Riemann sphere. But of course, you can completely deduce exactly as here you can deduce the dynamics of the vector fields by a first written map. In the complex situation, you can completely understand the dynamics of a linear differential equation by a representation of the T parameter space to the groups of Möbius transformations. And so Sullivan completely understood the representations in the Möbius groups that are structurally stable. And in fact, Dumas used this theory to produce these pictures. But as I said, so in the case of In the case of the of nonlinear differential equation like Jouanolou foliation and their parameter spaces, it's very hard to produce a picture, and I think it's a challenging problem. So as I promised, I will finish with this, so a conjecture in any degree. So I think in fact, we have experimentally we have verified this transversality, so the fact that these critical points in any degree they have local minima, not for the norm, Hermitian norm. It's not true, but you can change the norm by taking a Hölder norm, which will satisfy this for degree. We have verified this till degree 6. And so we have this conjecture. And also, as I said, so we have a kind of precise conjecture for the combinatorial structure of the Julia set. And it resembles, and I will finish by that, it resembles this limit set resembles an attractor of that that was discovered by Lorentz. So this is an attractor of a differential equation in the real case. So in 3 real dimensions here, x, y, z are real, so it's no more homogeneous, so maybe notation is not very good here. And so this is the differential equation. In fact, Lorentz observed that if you take a generic point with respect to the Lebesgue measure, then the trajectory is going to have as accumulation set this what is called a butterfly, this picture, which is called butterfly. And in fact, it has a very precise combinatorial structure. So trajectories turn around these two sides kind of randomly, but you can make all this kind of precise. And it is I think we have a conjecture that there is a kind of dictionary between these limit sets of the Jouanolou foliation and this kind of butterflies. Okay, I will stop here. I thank you for your attention. Thank you.